Hi, and welcome. Thank you for the opportunity. So I want to talk today about the benefits of microfluidic cell processing and how it can dramatically improve the starting material for autologous therapies, and also for allogeneic starting material as well. In a nutshell, it's better. So obviously, we're pre-commercial. We're going to be launching our system. You can see it outside at the first quarter of next year. But what is the mission of Curate Biosciences? Well, our mission is really to improve the starting material, to solve the fundamental garbage in, garbage out problem, if you will. The reality is today is not everyone can get treated. There are patients, various places around the world, where you cannot even get treatment in time. They cannot make dose in time. They are unable to live long enough to receive the treatments. There are evidence out there now with studies from Novartis and other people where the time in culture, the manufacturing cycle, is delimiting the efficacy of a drug. So if you can solve the problem of time and the quality of the starting material, you should end up with a better place for a better therapy. So the problems really, whoa, this is going on. The problems really are going on from its variability, its cost, its also durability, and its access. But the root cause of these is really the cell loss and the cell quality, and also the quality of your construct itself. But if we solve this problem, then the success, this is going on its own, should have a shorter process and a better product. So our vision then is to have improved outcomes and a shorter, more decentralized process. So what should the ideal cell and gene therapy process look like? It should allow us to recover the maximum number of T cells that are possible in the patient sample. On the left-hand side, what you have is a study done by the NIH in 2017, I think it was. But the green line represents 10 doses of Kymriah as a benchmark. So people start out with the right number of cells, but the process is sufficiently flawed that we're losing all the cells in the way. And so as a result, we have to expand them, shorten the telomeres up to make the engineering process work and deliver dose. So the ideal should recover all target cells. It should have a highly efficient washing process. It should allow them to concentrate. It shouldn't perturb the cells, shouldn't activate them adversely, shouldn't differentiate them. It should have an expression or expansion possibility that allows them to grow if you need them to grow, to get the successful dose equivalency in a short amount of time. And if you do that quickly, then you should have functionally dose made sooner, and it should have a better quality. So what's the current reality? Current reality, this is, again, a study from the NIH, where they looked at 6 studies in retrospect, and they looked at various methodologies, whether it's a bead-based selection or a non-bead-based selection, to get the starting material. And on the left side of the middle panel there, you see fresh process samples. You can see it's around 60-something% efficient on a good day, but it can be as low as 30% efficient by the time we look at the cells recovered. And the distribution of that is significant. If you look on the right-hand side of that multicolor panel, you have what happens when you freeze a sample. The recoveries drop on average, and the distribution, the variance goes up. So we're starting out, if we're using cold chain logistics, from an inherently bad position when we're processing a sample that's being manipulated after it's been frozen and then thawed, because all the biological milieu that's still present during the processing steps and the complications around recovery with all the existing technologies are driving cell loss. And so you can see as little as now 20% recovery for a starting material. So what if you could start here? So this is, in a nutshell, what the benefits of microfluidic processing can do. We can start at the beginning. And so the machine outside will show you, we can process, using microfluidics, using a closed system, an entire leukopak with about 10 minutes of hands-on time in under an hour. So that's 40 billion cells an hour processing rate for those people who are counting. It's a 90% efficient system, but the core technology behind that is actually operating at 96.5% efficient. The wash efficiency is about just 3.5 logs, depending on what an analytical metric we use. And the recovery and the white cell removal is unsurpassed. How it works, as you see this little video cartoon here of a system, is what we do is we have a series of multi-parallel arrays which have a lot of microposts. We have about 3 million microposts, 10 by 20 microns by 50 microns deep, all sandwiched in this single-use consumable. We set up laminar flows where we pass red cells and the apheresis undiluted through the product, and large cells migrate, as you can see, down these channels towards the central channel. And we do this in a massively parallel way. And so the leukocytes roll straight through, the red cells roll through on their short axis, and the platelets go straight through. So the net result is exceptionally clean leukocyte preparation, as you can see from the pictures there. The white cells are truly white. There's no pink tinge to them at all to speak of. Platelets are essentially devoid, and there's no red cells left over. And we do this, of course, without pelleting the cells. So this is fundamentally a good starting point. The left panel here is the array efficiency, 96.5%. So it's this processing efficiency. We dropped our recoveries down to about 90%. This is all because samples come in, and most of our data is at 24 hours with ambient storage and shipping. So we lose about 10% on average to the shipping process. The actual array itself is processing around 96.5% efficiency. So that drives really consistent and robust performance across both cell selection as well as concentration of leukocytes. And as you can see, the plots there I have the recovery, depletion, viability. Those groups on the left and the right side, irrespective of the mode of operation, are statistically identical. So we don't have any negative impacts associated with an extra processing or concentrating step. We get rid of the pre-processing filtration that most people are doing, integrate that into a single workflow, and drive to a very robust solution that gives really robust performance across all modes of operation with exceptional recovery. And the recovery of this is, compared to here we're using manual FICOL because it's what everyone has benchmarked against. We get about twice as many cells in this particular study as of T cells. We actually see more than twice as many. And this is because a FICOL, when you make a FICOL preparation, you get rosette formation, and you get naive cells dropping through into the granulocyte interface. And so what we've done with microfluidic processing is essentially eliminate the need to co-locate the cells based on density. We separate basis off size, and that allows us to have an exceptionally clean product. You can see on the purity side, less red cells and less platelets. We've actually seen as much as 32-fold fewer platelets from some of our test evaluation sites. In addition to this phenomenal recovery, it's unparalleled, and then purity, we also see biological benefits. So I talked about rosette formation. We are not actually seeing the naive cells and central memory cells pass through in the rosette forming process. So we recover, as mentioned, more than twice as many of the T cells. And the T cells, of course, are the naive and central memory are what matter for a CAR T preparation. And so this has been consistent. We have more CD4 cells, more naive cells, and we get better washing. So this is the washing data. 3 logs we spiked in this example, baculovirus into whole blood. We've also looked at fluorescinated albumin and not separated out the free fluorophore, get a very efficient washing. And the benefits of this washing, in addition to removing the co-stimulation that comes out of platelets being around, is less activation. So this is looking at CD69 on T cells as an example. So half as much activation of cells. So we get you the maximal recovery of the T cells, the most quiet cells possible, to begin the next step in the engineering process. So when you think about a CAR T process in particular, we just heard about the importance and relevance of Tregs. Because of removing the platelets and preventing the co-stimulation, you're preventing, and you're also removing highly efficiently the TGF-beta, all the other pro-inflammatory molecules that are present in even just an hour of incubation in a FICOL presentation. So we have data, I'm not showing it here, but we have data proving that that add back is enough to cause premature differentiation of T cells. So if we remove that by efficient washing, we prevent the generation of Tregs, which then take more naive cells away from the Treg pool, prevent the expansion of more Tregs from the self-renewal prospect of Tregs, and then you also have the benefit of having less of the Tregs impeding the expansion of the T cells. So we get better quality product sooner, so we have more cells coming in and less Treg generation. The other nice thing about a nice clean wash is that cells are better transduced. So microfluidic processing really allows us to eliminate all the platelets, which will naturally take up the virus when you introduce it, if there's any residual platelets still there. But we do this without losing cells in the first place. So we have more cells that you can put virus onto. So this on the top panel is looking at a GFP, lentiviral GFP construct, where we see 50% or more advantage even at day 6, but we don't need to go that long, and I'll get to the punchline in a second. We've also shown here that we process cells and we freeze them, ship them to a collaborator over in Maryland at Dr. Tanakovic's lab. He makes CAR-Ts, freeze them, thaw them, and then assess the functional capacity and expansion, and we see nice central memory cells being developed, as you'd expect and as you'd hope. This is just gated on lymphocytes on the far right panel. These cells do expand as you'd hope to see them. So on the left panel, this is an N of 20. We're looking at our internal studies, comparing how well we expand from a total recovery basis as compared to how many cells we get from the Curate processing. And the green line, again, is the Kim-Ryan line. So we start out with recovering 10 doses equivalency. So this speaks to the need to do I even need to expand these cells? I'm not sure. But on the right-hand side, you have a sample that we sent to Dr. Tanakovic's lab, where you can see actually that in this particular example, the cells expanded preferentially compared to the FICOL. So we're seeing good expansion, good recoveries, less perturbation of activation, better washing, and we also see good kill. So this is following on the story from Dr. Tanakovic's sample, where we're going from the clean and freeze, if you will, from the clean all the way through to the patient journey. The cells are fully functional. They kill with luciferase assays. They're specific based on the ELISpot data, and they're releasing the normal kinds of cytokines that you'd expect to see. The nice thing about all of these synergies is that we will have recovered all the cells, prevented the degradation of premature differentiation and the loss of cells going to an energic process. We'll have complete transduction, more efficient transduction, and that will allow people to make dose sooner. The data we have internally on normal donors says it's at least 3 or 4 days shorter. So this is where we get to how we can improve the process. It's really about improving the quality of the starting material with all the existing technologies that are out there that will really allow people to drive a better solution. So if you get the cells, you keep them in good shape, then you get to a better outcome. And I think everyone in the room has talked at some point about how good quality starting material really impacts all things downstream. Well, it's true, and this is what we're experiencing and seeing in all our data. So in summary here, we prevent the damage associated with current processes based upon density-based separations. And that highly efficient microfluidic processing addresses the pro-inflammatory cascade, it addresses the cell loss, the bias of cell loss according to density-based approaches, and that has benefits on transduction and expansion, and the killing is not affected, as you've just seen. So our thought is that we solved the vast majority of the problems that are coming out of the variability, the cost, and therefore the access to patients should be improved if you adopt this technology. And increasingly, it's evident with the Treg story and the shorter time in culture that we may even have an impact on the durability of the treatment itself. So on the right-hand side, you see the distribution of samples of this N of 50 approximately compared to the FICOL arm in the direct comparisons. And so if you're going to develop a manufacturing process, do you want to start at 12%, or do you want to start at a minimum of 73% recovery? Now, it's not just me saying this. We've done this with external collaborators. And on the screen here, you see a 4-way split done by a CDMO, who I can't identify, and the technology you can see there on the screen are probably self-evident to everybody. But you can see our microfluidic separation, deterministic separation at the top, clearly is unparalleled in terms of its ability to recover the cells. And you can see from the product, it's very, very clean. But the important thing is this is very, very easy to use. The customer has to make an addition of an enzyme for a pretreatment protocol. They run the sample by adding volume, adding the cell counts, accessioning the system, pressing a button. And that is all they have to do. At the end of the hour-long process, you end up with a cell product that is unparalleled in terms of quality, recovery, and its ability to be used for next steps. So our vision, therefore, is to drive this to a point-of-care solution. So the right thing is to protect the patient sample. So by having the patient first in your mind versus a selfish interest around preservation of workflows in people's schedule, the right thing to do for the patients is to actually have a freeze collection followed by a cleanup and then a freeze, and then do whatever logistics makes sense. This will allow people to get the very maximum out of their patient sample. So with that, I'd like to close and say thank you. Any questions? Well, I'm out. Guess I'm out of time. Okay.